Yeah, so thanks for inviting me. I think I once gave a talk for Nessie back when it was a workshop, and it was during COVID, and I was so sad to give a remote talk for a conference that was supposed to be in Crete or some lovely location. But I'm glad I get to do this over again in another nice location. Okay. So I want to talk about symbolic reasoning in the age of large language models. And, I want to motivate why I do neurosymbolic AI, which is a little silly because I think, we share a lot of this motivation. But I also like to think about ways of telling the outside world why what we do is interesting and important. And so this is how I these days talk to the outside world when I try to present neurosymbolic AI. And I know we're close to Silicon Valley, and if I, probably leave this auditorium and talk to a random person and I say I do reasoning in AI, then they have a very specific idea of what that means. They think that I'm building chains of thought and that I'm really doing inductive reasoning from a lot of data. I've looked at a lot of mathematical proofs and I've trained a transformer to mimic that type of reasoning. And this type of reasoning is correct on many problems, which is why people are so excited about recent AI developments. But it's correct only on many problems, not on all problems. And you don't really know when it's going to give you the right answer. You just hope that this time it got it right and you can trust the result. But also why we're very excited about AI these days is because you can ask any question you like. Whatever you want, if you can write it in English, you can ask the model to reason about this problem. And second, it will always give you an answer. It might be nonsense, but it will always give you an answer. And this is in contrast with reasoning the way that I was taught to do reasoning 15 years ago, which was reasoning with symbolic AI. And so, as you know, this was logic and probabilistic reasoning, but crucially, it was using deductive reasoning algorithms that if they gave you an answer, it was guaranteed to be correct. The algorithm is correct, so it is correct on all problems that it could solve, but it could only solve a very, very small set of problems, those for which we had algorithms. Plus, those for which we had algorithms that would actually give you an answer before the sun burns out, right? And so this was why maybe we kind of got stuck with just symbolic AI. And the motivation of my work today is, what is there in these old ideas from 30 years ago that is still relevant today, and can we actually fix the problems we have today when we say we do reasoning in AI Silicon Valley style using these older ideas? Okay, so the questions for this talk are, do these old ideas still have a purpose? And I mean, of course, I wouldn't, if I would say no, then you would chase me out of the room, so I hope to convince you that yes. But I also want to go a little bit into what does reasoning look like today? How did we kind of change the reasoning algorithms to actually be compatible with kind of modern AI. And then last, I want to talk about kind of maybe the most glaring gaps in modern AI and how deductive reasoning algorithms can help address those. Okay, so let's get started with the first question. Why do I still care about these old ideas? And so here's a little motivation. This is actually an example we came up with a couple years ago, but it turns out it's still relevant today. I just want to generate a sentence using the words frisbee, caught, and dog in that particular order. And say that I ask GPT 4.1 mini, which is a model that's not that old, a couple months old, I guess, 6 months old. And it says the frisbee flew through the air and the dog caught it with excitement. It's a beautiful sentence, but it doesn't actually do the right thing. It got the order of caught and dog wrong, okay? Okay, let me download an open source model, Llama 3.23b. It's one of the smaller models, but also kind of from the last year. The energetic dog leapt into the air, caught the frisbee, da, da, da. Beautiful sentence, but again, the order of the words is wrong. And so what do you do typically when your LLM doesn't do what it's told? You say, please do the right thing. You got the order wrong, make it right. This is the typical loop that, a lot of folks are doing now, right? They're getting an answer from the LLM, they're finding the mistake, they're putting the mistake in the prompt saying, don't make this mistake, and you hope that eventually it will get it right. In this case, you say, give me a better answer, fix the problem, and it actually gets it wrong again. Now the order is completely in reverse, dog catch frisbee instead of frisbee caught dog. Okay, so this is, years into this example, still like a relevant example. And so what I'll present to you is a system that came up with this answer, which is the obvious one we would all come up with. The frisbee is caught by a dog. That's very straightforward. But then also, as part of its samples, you can find these beautiful creative answers like a pair of frisbee players are caught in a dogfight. which I thought was a beautiful response here, and also satisfies the constraint. Okay, so let's look a little bit more mathematically at what's happening here. We need to generate text, which means we need to sample from the next token distribution of our large language model. And we are given a prefix. And here I'm going to simplify the example. Let's just say the prefix is the weather is. And we have a constraint, a lexical constraint, which says what is the thing we want to achieve as we are generating the sentence? What are we planning to do later? And here, let's just keep it simple. One keyword, winter. Okay. And so this is going to be the constraint alpha. And if I now want to generate from this distribution, I need to actually sample my next token, given the prefix and given the constraint. Okay, this is just how, in the language of probability, we write the task down. Now, there's actually an easy way to solve this, and luckily, Reverend Bayes told us, I don't know, 300-400 years ago how to do this. How do we reason backwards in time? How do we invert the arrow of causality? Well, Bayes says, apply Bayes' rule. And here you see Bayes' rule without its denominator, which is irrelevant here. And Bayes' rule says that if I want to generate from the next token distribution given a constraint, I can just first look at what is my next token distribution, ignoring the constraint altogether. This is my next token given prefix, the blue part of the equation here. And then I need to scale all of these choices of next token by the probability of achieving the goal if I were to choose that next token, okay? Which is the probability of alpha given next token and prefix. This is really just Bayes' rule without the denominator, which is a constant. And this is nice because this tells us that we can take our next token distribution from our LLM, the blue part, and we just have to rescale it in order to do the right thing and to reason probabilistically about how do I achieve my goal. All right, let's look at an example. The weather is cold or warm, maybe with equal probability by the large language model. If I say cold, it makes it much more likely that eventually I will say winter. If I say warm, it's going to be less likely that I say winter later on. So the probability of achieving the goal is much higher if I were to choose cold. And now what I need to do is I need to multiply element-wise these probabilities, and I get this distribution here, which if I normalize it, gives me the correct Bayesian posterior of the next token distribution given the constraint alpha. And now if I sample from this distribution, I will actually achieve my goal. Okay, make sense? All right, so this is one example. Let's look at another example. So right now in Silicon Valley, billions of dollars are being spent on alignment, quote unquote, which means how do I get my large language model to do the right thing in some vague sense? And maybe a simple form of alignment is to say, I want my language model to say words that are non-toxic. Okay? If I just pre-train on the internet, a lot of stuff is going to be toxic. Half of it is like weird Reddit posts. And I somehow want to train on them in pre-training because they give me information, but I don't actually want to just regurgitate them at test time. That's why I have post-training. Okay. All right, same equation. Reverend Bayes comes to the rescue, and Reverend Bayes says that if I want to generate next tokens that are non-toxic, if I want to not even just generate next tokens that are non-toxic, if I want to generate entire sentences that are non-toxic, what I need to do is look at my next token distribution, which could be very toxic, and then I need to also look at this red equation. And the red equation here is saying that, well, there's actually a difference. If I say it's a pain in versus it's a pain to, the completions that I get afterwards are very different. If I say it's a pain in, it's going to be likely a pain in the ass, a pain in the butt. It's not so nice. Maybe not the most toxic thing you can think of, but maybe the most toxic thing I'm willing to put on a slide. Okay? If I say it's a pain to, it's going to be very mild. It's a pain to deal with. It's a pain to handle. It's very, very kind and nice. So it's a very different probability of generating something non-toxic depending on these two choices. And that's what's captured here by this red number. If I say it's a pain in, the probability of non-toxic is much lower than if I say it's a pain to. All right, so Reverend Bayes says element-wise multiply these tables. This is your new table, sample proportionally, and now it actually makes it much more likely that I would say it's a pain to than it's a pain in, even though the pre-trained model might like to say it's a pain in much more. Okay, so I've kind of corrected this bias towards toxicity by doing the Bayesian reasoning. All right, so that's another example. And I'll get into this one in the third half of the talk, third of the talk. Okay. All right, so reasoning about all future tokens, let's apply it elsewhere. Let's say that I'm developing a self-driving car. And one interesting way of doing control of such a car is called offline reinforcement learning. It's a very simple idea. It's saying, let's look at all the drivers in Santa Cruz, and let's look at all of the states and actions that they find themselves in as they drive around, and maybe also collect their rewards, meaning are they hitting other cars, are they getting to their destination in time. Get all of the data of all of the drivers and just train, let's say, a transformer to predict, given the previous state's action rewards, what are the next state action and rewards. Okay, so that's called offline reinforcement learning, but there's a big problem with offline reinforcement learning, which is that an average driver could be really crappy. Santa Cruz has changed a lot since they were driving around there. And I actually I really just want to mimic not the average driver, but I want to mimic a good driver that also understands that certain roads have been closed, that I don't really want to do the dangerous things that I see out in the road, etc. So what you have in practice is, in offline RL, is you have a bunch of constraints about the future. I would like to know, what does the average driver do as their next action to drive this car, given that they will reach their destination on time, that they don't bump into other cars, that they don't accelerate too fast, that they don't find themselves in a state where the car is, I don't know, stuck in a ditch. Okay? So there's, again, a lot of stuff I want about the future as I'm trying to determine what is the next action I'm going to do right now. Okay? Seems very familiar at this point. Again, Reverend Bay says, my next action, given my prefix and my constraints about what I want about the future, is just what the average person would do, the blue part, times the probability that I actually get a good outcome at the end. All right? Same equation. Okay, now you start to see a pattern here. So I feel like I'm almost sufficiently motivating this problem. And we'll get into these applications later. Okay, so what do they all have in common? They have a language model that is conditioned on alpha, which is really just a language model that doesn't know anything about the constraint times this probability of alpha. And now here's the problem. This is completely intractable. No one can compute what is the probability that Llama 3 says Santa Cruz at the end of a sentence. It's Sharpie hard. It's completely impossible to approximate with any guarantees. This is impossible, and this is why you wouldn't necessarily formalize your problems in this way, because it does seem like an impossibility. Looking 20 tokens into the future means you have to look at more sentences than there are atoms in the universe. So that's not going to happen in a naive way. Okay, so now comes a little bit of a sleight of hand where the solutions that I will provide are abusing Bayes' rule, if you like. They are saying that whenever we need to reason about the future, we cannot use the large language model, completely intractable. However, suppose that we can find another generative model, which we'll call circuit here, that actually does allow us to compute this probability alpha, then I can assume that if this circuit is close enough in KL divergence to the language model, if they're similar, then I get a very good sense of what the language model would do in the future, just by having this circuit available to me, this tractable model. And you can think of it as some kind of digital twin. It's really supposed to be the same as the language model, except it can do symbolic reasoning. Okay? That's the goal of this extra circuit model. And the second part of my talk will go in a little more technical detail of how, what these circuits look like, how you get them, how you learn them, and so on. Okay, so for now, just believe me that I can compute this number using some oracle, this digital twin for symbolic reasoning. Okay, so let's look back at our applications and let's look at the first one, the one where we have logical constraints we want to impose on the language model's generation. And here I want to be a little bit more precise about what it is we're doing. When I say I want a logical constraint on my generation, I can actually think of this as a DFA. So a DFA looks like this. It's a state machine where initially you're in some initial state, and as you generate more tokens, you move around in this finite state machine where you say the weather gets cold in the winter, and now I'm in an accepting state, and that means that I have satisfied my constraint. Okay? So I will assume that whenever I need to generate something, there will be a DFA that tells me what it is that you want to generate. It's pretty flexible. You can do a lot of things with DFAs, say that things must not appear some number of times. And honestly, over a finite sequence length, which is anyway what we do with LLMs, you can really write anything in theory. In practice, I guess the size of the DFA depends on what you want to write. Okay. The reason why we care about DFAs is because you can show that if you have this tractable digital twin, which again I will get into later in the second part of the talk, you can actually prove that you can compute this probability of achieving the goal, the probability of alpha, in time linear in the size of this tractable digital twin, the size of the DFA, and the sequence length. Okay? So very efficiently, you can actually get a sense of where you're going as you're generating the language. Okay? So more about this later, although it's a very technical topic, so maybe not too much. Let's try to apply this idea now on some benchmarks. And so this is the simplest benchmark in this space. It's a little outdated, but it kind of gets the intuition right for you. So this is called Common Gen. It asks you to generate sentences with a bunch of keywords, kind of like the first example. For example, snow, drive, and car, and then there's some answers that are reference, gold standard answers, like a car drives down a snow-covered road. These constraints are interesting. They're actually kind of like CNFs, where you can generate, you have to generate each of the keywords, but you can generate them in any of their inflections, and there's many inflections of the same word. And so here's some results compared to the state-of-the-art for what was GPT-2 at the time. This Control-G framework generates text that is much more realistic and closer to these reference answers, and also generates these sentences with 100% constraint satisfaction, meaning it always guarantees that whatever keywords you want will appear in the generated sentence. Okay, so this is kind of the first sanity check that this works. Okay. But we want to be more ambitious. So what we said was, you know, it's scary to deal with the big bad large language model world, and you know, in the neurosymbolic AI world, we're sometimes very happy to kind of stick to our little benchmarks, and we don't really want to compete on the turf of large language models, right? But we said, okay, let's try to be brave, and let's try to find an application there where everyone agrees, like, this is the bread and butter of large language models. This is what they're supposed to be good at. And if we're able to outperform them there with neurosymbolic methods, then maybe this is a significant claim to make. Okay? All right, so what we did was we took creative text editing, so basically creative story generation, which I think we all agree is the bread and butter of LLMs, right? Write me a story about Shakespeare in Santa Cruz or whatever, right? So you can do whatever and it can come up with a beautiful story. Now, we wanted to show that neurosymbolic methods really help with this particular process. And the task at hand is we've already written a story, but there are certain parts of the story we're unhappy with. In this case, we have this, this paragraph, and we're not happy with the blank, so we say delete the blank, and we want to put something there that actually fits better with the story. Okay? So the story is, first they've defeated a small squad, blank, and then there are a few humans left, and et cetera, et cetera. And the task is substitute for the blank something that mentions the words alien mothership, far from over. These are not just tokens, but phrases. Of course, it has to fit with what comes before and what comes after. And also, we want the generated text to be 25 to 30 words, right? We don't want to end up generating too much or too little there. Okay, so we turn this into a DFA, which is pretty easy to do. We start cranking the next token distribution conditioned on the DFA, and this is what we get. They've defeated a small squad of aliens, where you already see that there's the alien mothership is already being used. It's already working towards saying alien mothership, which it does later on. The problems are far from over. There are a few humans left, also fits nicely with the end of the story. So what happened here is that Control-G, which is the system I described, is able to really nicely fill in these gaps with the right keywords and length and make it all make sense. Okay, so this is one example where it looks good. So let's properly evaluate this. Let's do a human evaluation study. And so here we look at different models and how they handle keyword constraints, length constraints, and both keyword and length constraints, which is the last column here. And we asked humans to rate with stars, how much do you like the story? Is this a good creative writing exercise? And actually Control-G outperforms GPT-4, which was, I guess, the best model at the time, a year and a half ago. And people actually liked what Control-G said much better. Here we're measuring how often does the system actually do what you're asking? How often does it include the keywords that you ask, like alien mothership? How often does it stay within the bounds of the length constraint? And so here Control-G does a good job 100% of the time. GPT-4, especially with keyword and length constraints, only 27% of the time is actually doing what you're asking it to do. Okay? And of course you could ask, like, please fix it, and it might get a little better. But fundamentally, it doesn't really know what it's doing there. And then the overall evaluation is how often do we generate something that looks like a great story, like 3 stars or up, and do we follow the instructions that we're given? And just to make a little bit of a flashy claim here, Control-G gets it right 82% of the time, GPT-4 14% of the time, and I think this is kind of shocking because I don't know how much money went into GPT-4, while Control-G is a tiny open source Llama 2 based model with a DFA on top and Control-G to do the decoding with probabilistic reasoning. It's extremely cheap, extremely kind of basic setup. And the real takeaway here is don't be scared of the big bad LLM world. With neurosymbolic methods, you can really make a difference on the applications that are maybe in the enemy's turf, right? So I think that's the takeaway here. Okay. Everyone's obsessed with reasoning these days, and with reasoning they mean this type of reasoning, right? Since DeepSeek, this is what the world talks about. How do we get LLMs to prove mathematical theorems, or in a basic level, do high school math or grade school math? So here we have a question, and you can recognize these data sets, right? And it happens to be so that the vanilla LLM actually gives the wrong answer on this question. It doesn't really matter, it has a chain of thought, it computes some numbers, and it gets 24, but this is not the right answer. And we said, oh, let's try to get Control-G to actually solve these benchmarks. So Control-G gave a different answer. It looks like a different chain of thought, a different computation, and the answer is 64. And Control-G is really the same thing as a baseline large language model, except it has a DFA that guides its generation, that says where it should go. And so the question for you is, do you see what DFA we applied here? Of course, the DFA is not saying, like, you must say the answer is 64. That would be cheating. Right? Without knowing the answer, we found a DFA here that actually improves by some percent the accuracy on these reasoning benchmarks. Well, it turns out that this DFA that we used here it's very simple. It's just saying every number that is mentioned in the question, you should mention at least once in your chain of thought. Maybe some number is irrelevant, that's fine. Right? You can just say the number 60% was mentioned, but is not relevant, right? You can attend to it and say, I don't care about this number, but you must at least mention every number once, because if you don't even mention a number, then somehow you're not taking it into account, okay? And so this is a very simple DFA. It's a different DFA for every question, but if you impose it, you improve your accuracy, okay? And there's many more things I'm sure you can do with reasoning, but this was just the first simple thing we tried, and it immediately gave us a boost in performance. All right. So this wraps up the first third of the talk. We are doing something that's really close to home for neurosymbolic people, which is logical reasoning, imposing logical constraints. And I didn't say it literally yet, but it so happens that whatever your tractable circuit approximation is, whatever DFA you're asking for, this constraint is guaranteed to be satisfied. Okay? And it's a very powerful property. And the reason why it's guaranteed to be satisfied is that if you were ever to consider a next token that makes it impossible to satisfy the constraint, then the probability of generating that token would be 0 no matter what the language model thinks. Okay? And it just boils down again to Bayes' rule. if I'm about to use a next token that makes it impossible to satisfy alpha, then no matter the distribution P circuit, the red probability will always be 0. And I will always zero out that option. Okay? And so that's why it's no coincidence that in all the experiments I showed you, Control G had a 100% success rate, because it cannot fail. Okay? Okay, second maybe takeaway point is that when people talk about reasoning, they write all these papers where they train their model on reasoning benchmarks, right? That's what billions of dollars are spent on. And these things tend to work okay if at test time the questions you ask are from the same distribution, almost identical distribution to the distribution of reasoning tasks that you trained on. As soon as you change a little bit the distribution of reasoning tasks, these things start to break down pretty quickly. Okay? And you might wonder, is this true of Control G? Is it true that if I ask different questions than at training time, would it also start to break down? And the answer is no, because it has never seen any reasoning task at training time. We have a large language model which doesn't know about any keyword constraints or DFAs. And then we've trained this probabilistic circuit, this digital twin for reasoning, to just be as close as possible to the large language model. But it has never actually seen what type of reasoning it's supposed to do later on. The reasoning only comes in at test time, and this is a beautiful property of good old-fashioned AI, is that you build your SAT solver and it's going to work correctly. You don't have to know what is the distribution of SAT problems I'm going to actually be training on, be using at test time. Sorry. And so everything is unseen and it works robustly regardless. So it also means we don't have to train on a distribution over tasks, which is kind of the expensive part, right? This is why it actually does cost billions of dollars to train LLMs to do reasoning, is because you have to actually learn what is the distribution of reasoning tasks that my user might care about. And then the third takeaway here is that you might have heard of tools like Outlines and so on, SGLang. I can ask ChatGPT. OpenAI gives me an API in Broeck where I can ask, generate correct JSON files. So there's a lot of tools out there that do structured generation. And they're actually very different from what we're doing here. If I ask a structured generation tool, generate a sentence with the word Nessie, it will say, the weather in Australia is sunny and Nessie. Right? It has no way, when it starts generating things, it has no way of actually building up to achieving the goal. It will only achieve the goal at the very end when it has to. And so that's why these existing structured generation tools are very brittle, and you can only really use them for like grammars and things that are, it's pretty clear what you're doing already from the beginning. Okay, so summary of this part. Even though you have an intractable deep generative model, you can have this tractable digital twin for symbolic reasoning that allows me to do this cool neurosymbolic stuff correctly and in a way that's very effective. Okay, second part of the talk. Okay, so to do all of this, we're not just calling a SAT solver or a Bayesian network inference algorithm on the CPU and waiting till the sun burns down, right? We're doing something different here, which means that all of this stuff runs on the GPU. It has essentially no overhead. I think in some of our experiments, it's like 10% slower than just generating from the language model without any neurosymbolic stuff. So how do we fix the old problems with reasoning algorithms in AI? And so this is kind of the big picture. When we talk about generative models, you can think of the old school stuff that's really inexpressive, things like naive Bayes, Bayesian networks, Gaussian mixture models. And these are really very much not in fashion anymore. And then what we're all excited about today is diffusion models, transformers, and so on. And it's true that traditionally these models were much less expressive, but they actually had one benefit, which is that they did allow you to compute things like the probability of this constraint alpha, the probability of a DFA, if you want. Okay? So they were actually more tractable for symbolic reasoning, while today's models are very much intractable. And so what we've been doing for maybe a decade or more is trying to get these architectures of the olden days and try to make them scale on the GPU to the point where they're actually both expressive and tractable. And so these we would refer to as circuits, but you can really think of them as massively over-parameterized, very, very large instances of these classical architectures. And I don't, you can find like a 3-hour tutorial online if you really want the gory details, but at the high level, these things are actually very simple. What they're doing is they're taking a joint probability distribution, like this table here, over 3 random variables, and they're saying, let's write this table not as a table, but as a polynomial. So you can check for yourself that if you plug in some row of this table into the polynomial, let's say 0, 1, 0, I plug in 0, 1, 0 for x1, x2, x3, then the polynomial will evaluate to 0.1, which is the probability of that world. So this is a representation of a joint distribution. Now, the reason why this is unappealing is because if I have 20 tokens in a large language model and I want to represent this with a polynomial, I need more monomials in this polynomial than there are atoms in the universe, so that's not going to work. Okay, so the first trick that's kind of crucial here is to actually turn it into a deep generative model. The way we turn it into a deep generative model is to say that that same polynomial that is exponential size can be represented compactly if I write it as a circuit. I just multiply and sum little polynomials to get a more complicated polynomial. And now, with a very small circuit, ideally linear in the number of random variables, I can represent this distribution, this table with exponentially many possible worlds and probabilities in it. Okay, so that's the first takeaway. And this is already a generative model, meaning I can compute a likelihood, for example, right? So here's a simple polynomial circuit for a distribution over 3 pixels, x, y, and z. And if I want to compute the probability that the first pixel is blue, second is yellow, third one is orange, or whatever this is, I plug in some zeros and ones into the polynomial, telling me what is the world that I'm currently in. I compute sums and products of these polynomials to get bigger polynomials. And at the output of my circuit, I get the probability of this world. Okay, so very straightforward. Okay, so now I have a deep generative model. It's called the probabilistic circuit. But there's actually more that I want, right? I need this probabilistic circuit to be tractable for reasoning. And when I say reasoning, symbolic reasoning here, I'll very specifically mean marginal inference. So marginal inference is the task of computing the sum of a bunch of rows in this joint probability table. So here I want to know what's the probability that x1 is 1, and I want to marginalize over x2, which means I have to sum the blue and the green number, and I need to compute 0.7. This is just a simplified version of exactly the task we needed in Control G. In Control G, I need to ask, if I sum over all the future text that I could generate, if I would sum up the probabilities of all of the sentences I could generate where alpha is true, what would it sum up to? Okay, so this is called marginal inference. And it turns out that these deep generative models that are just polynomials don't allow you to do that. So we need something extra. And that something extra is also very simple, actually. It is the property that these polynomials are what's called multilinear, that they never multiply a variable with itself. If I look at the flat polynomial representation, you don't see any x1 square or x3 cube or whatever. It's always just to the power 1 or to the power 0. And this is called multilinear. And then it turns out that, and you can check this paper by my student Oliver, it turns out that whenever you have a multilinear polynomial, however you represent it, you can always compute a marginal probability in time linear in the size of this polynomial circuit. Okay, so this is kind of the high-level story, and there's many gory details here that I'm hiding, but at least hopefully you can kind of see the picture here. Okay, so what did we do in practice to solve Control G to wipe the floor with GPT-4? We did something very simple. It turns out that if you take this 60 or more year old idea of a hidden Markov model, which I guess we all learned about if we're as old as me, 15 years ago, when hidden Markov models had like 3 states and 5 emissions and like 20 parameters. If you take the idea of a hidden Markov model and you massively scale it up on the GPU, you give it 32,000 hidden states, 2 billion parameters, then what this hidden Markov model is actually computing is a multilinear polynomial in its algorithm, its forward algorithm. Okay, and so you can train this on the GPU, and now you have such a tractable digital twin. It is one of these probabilistic circuits. And I already told you this theorem that if I have a DFA and I have this tractable circuit representing the hidden Markov model, then in time linear in each of them and the sequence length, I can compute the probability of my constraint. All right, so this is kind of roughly how it works. Okay, there's a lot of stuff we had to do, lots of blood, sweat, and tears to make this work, and also on the system side. So one of the issues is that there's this hardware and software lottery that you have to play. Unless your architecture today is very well supported by NVIDIA GPUs and PyTorch, you're dead, okay? And so what we had to do is actually write our own system as, you know, an alternative to just vanilla PyTorch that actually implements some CUDA kernels in Triton that actually does the training of these probabilistic circuits very efficiently, so we can actually train a 2 billion parameter tractable deep generative model. And so this is called PyJuice. There's a lot of really good probabilistic circuit tools out there by some clever folks, but actually by writing these custom CUDA kernels, you can be orders of magnitude faster and more scalable. You can check the details in the paper, but it's like orders of magnitude really faster. And then we're actually very proud. So Google actually has this Dynamax system, which it's not really for probabilistic circuits, but it also is able to learn hidden Markov models, for example. It's kind of at the intersection of what both of these tools support. And if we look at hidden Markov models, then PyJuice is about, 100 times faster than the code that the folks at Google wrote. So pretty proud of that. Okay, so that's the system side. On the architecture side, this is something we did after the Control-G paper, but this is kind of the state of the art now. Some of these older ideas, like hidden Markov models, they're a little naive if you look at them from a modern deep learning perspective. For example, in a hidden Markov model, you have what's called the transition matrix that takes you from the previous time step to the next time step's hidden state. And if you have 32,000 hidden states, that means a 32,000 square matrix of numbers that you're representing. It's a lot of compute for actually very few parameters, relatively speaking, because you have to do matrix multiplication. And so one of the exciting recent developments is that we're able to actually parameterize these linear transformations you do in these tractable deep generative models to actually be compute optimal and to actually have as many parameters as there are floating point operations in the computation. And you can check this paper that's using monarch matrices, which is also very popular in, for example, state space models and transformers. You know, these actually modern deep learning ideas are actually very useful to scale up these, you know, symbolic reasoning methods. And when we did this, so the blue line is the hidden Markov models loss. By just parameterizing these linear maps using a monarch transformation, we actually got much better results, and actually they became very competitive with flow and diffusion models, discrete diffusion models. So part of this game is also saying, if I design my architecture to be able to do symbolic reasoning from the get-go, then you can already say, oh, I'm solving a harder problem, so I don't need to be competitive in terms of the pure machine learning numbers. But actually, you can scale these things up, make them work better, and you can kind of compete even on just the machine learning numbers for people who just don't care about reasoning at all. Okay, so that's the takeaway here: is just be ambitious when you train your reasoning models. All right. Maybe a final remark here. So I started this talk by saying, we don't need just neural networks, we need reasoning algorithms, right? And now I told you that my reasoning algorithm is just another neural network that computes a polynomial, right? Just another feed-forward network. So I'm the embarrassment of the neurosymbolic community, where I just, I switched sides completely and I pretend like a neural network is actually running an algorithm. Okay, so you can check this AI stats ICML paper from this year, where we actually prove that if there exists an algorithm under the real RAM model of computation, a little different from a Turing machine, a real RAM model of computation, if there exists an algorithm that runs in polynomial time that can compute a marginal probability, like the probability of alpha, right, that I could be running on the CPU, right? If there was an algorithm out there, then there also exists a polynomial size circuit for that family of distributions that is multilinear. So by saying I use multilinear circuits, I'm actually not losing anything. It has exactly the same power of computation as any algorithm you could ever run on a real RAM machine. Okay? So this gives me a license to not be the embarrassment of the community, I guess. Yeah. They're really equivalent. Okay, so that's the second part of the talk. And then for the final part of the talk, I want to dive into some of these other applications that I mentioned as a motivation in the beginning. Specifically, I want to talk again about this alignment problem, right? So it's a pane in is much more toxic than it's a pane to. So this is a little different than control G. There's no logical constraint here. There's no lexical property. I cannot look at the token sequence and say this is like accepting or not accepting, okay? It's a bit more of a vague notion. But otherwise, it's similar because we do want a property of the future generation to hold. Okay, so let's look at it in some more detail. It's a pane in versus 2. The language model says in has probability 0.3, 2 has probability 0.1. There's a lot of red text for in. There are attributes, which in this case is non-toxicity. The attribute is not satisfied as much. It's more toxic text. There's a probability distribution over all these future texts, but the ones with high probability are all colored red. So we don't want that one. And again, the same problem comes up. I don't know how to compute the probability that if I were to generate something onwards, I'm going to get something toxic or not. It's completely intractable, Sharpie hard, impossible to approximate. So we need to make some reasonable assumption here to actually solve the problem. So here's the reasonable assumption. Similar to control G, I will say that my distribution over future text is going to be a tractable probabilistic circuit, like a hidden Markov model. Okay? Same assumption as control G. Second assumption I need to make is that when I classify things as toxic or non-toxic, I will use a log linear classifier on the tokens. So I will learn that certain words like ass and but, or making it more likely in this log linear way that you're generating something toxic. Okay? And now you can prove that I can compute the probability of generating something toxic, again, in time linear in the sequence length, linear in the log linear classifier size, which is fixed anyway, and linear in the size of the probabilistic circuit. So now very efficiently, I can say, for each of these choices, how toxic is it going to be at the end of the generation? Okay? Concretely, the expected attribute probability for in would be 0.1, for 2 it would be 0.8, so 0.8 is much better at generating non-toxic things. Reverend Bayes says multiply these numbers and now sample from this distribution, and now it becomes much more likely I sample 2 than in. Okay, so it works. Details of the algorithm are hidden here, but it works in a way that's not too similar, too different from control G. Okay, this approach to alignment actually has a bunch of interesting properties. So one of them is that the training time is essentially 0. It's just seconds. I can look at a data set of toxic and non-toxic text and train a log linear classifier within 10 seconds. It's a very trivial problem. If I want to do DPO on my model, which is what Silicon Valley is spending billions on, DPO, RLHF, all the variants, right? I'm going to train for a day or two on this size of transformer, okay? If I want to train an RL method that learns a value function, I'm going to spend even more time training some classifier that tells me for a partial sentence whether it's likely to be toxic or not. So this is just extremely fast. And at decoding time, it's also extremely fast. Because we have our tractable model, it takes maybe 10, 20% more time than just not using any neurosymbolic methods at all. If I want to, if I use something like DPO, it's also very cheap because once I've trained the model, at test time, it's doing the same thing as a vanilla model, right? But then a lot of these RL methods out there are extremely slow because they actually have to somehow compute this probability of alpha, even though they're not able to. So they have to evaluate a massive other model. They have to sample a lot. Some of the papers in this space are literally saying like, oh, at test time, we are like 10,000 times slower. And then like, what's the point, right? Okay. So it's extremely fast. Let's see how well it works, right? So this is fast, but simple because it's just a log linear classifier. So here we looked at a bunch of baselines, and most of them are actually using GPT-2, but we also included Gemma 2B here. And it turns out that in terms of toxicity, this is state of the art. So Trace, the model I described, is generating less toxic text. And there's different ways of measuring this in terms of the average toxicity, the worst case toxicity. In any of these, it is state of the art. And it's outperforming RL methods like DPO, PPO. It's outperforming all these decoding methods that are doing a lot of very expensive things at test time. So this is working extremely well. Okay, but there's many ways to cheat on this benchmark. So one way to cheat is to always give the same boring response, right? I can ask any question and the answer is I don't know. That's not toxic, but it's not very helpful either. Okay, so let's measure how diverse the responses are, so that I know that I'm actually giving you, I'm trying to answer your question. And also here, Trace is actually getting extremely diverse responses, especially compared to the reinforcement learning methods. And so this is something I briefly want to talk about. So if you look at the original language model, GPT-2 large, it has an entropy of 52. Okay, it has many ways of answering your questions. If I now use post-training to RLHF this model to be non-toxic, it will no longer be toxic, but it will suddenly say things that are extremely repetitive. For example, if I ask, tell me a joke, it will always be the same joke. If I say, draw me a picture of a red bird, it will always be the same red bird from slightly different angles. At some point, OpenAI was saying that people in Croatia like to downvote responses. They're a little grumpy, allegedly. And so at some point, the model just said, I will no longer respond in Croatian, right? And that's exactly what's happening with the RL methods for alignment, is that they're essentially giving up on the hard problem and only giving the easy answers, okay? And that translates into a massive reduction in entropy, okay? If you want to keep the full diversity of behavior of your model while still doing alignment, then something like Trace is a much, much better choice. Actually doing Bayesian conditioning for alignment instead of RL. So the story here is because I sometimes give this talk in Silicon Valley, and then I feel guilty because everyone there is working on DPO and all its modern variants, and they're spending billions of dollars, and then, I don't know, I feel like I'm slightly offending them, so this is my apology. Okay, maybe there's another way to cheat on these benchmarks. Maybe you can generate very diverse responses, but gibberish. If I just give random gibberish, it's non-toxic, but it's very diverse, okay? So how realistic are these responses? So that's the last evaluation, the fluency. And so here, among all methods that don't collapse the entropy, also Trace is extremely fluent in what it generates, right? So it kind of gets it right. It keeps all the behavior of the model, it generates fluent things, and it gets rid of all the toxic stuff. Okay. There's another fun thing you can do with this. So because it's so cheap to train a log linear classifier, we said, why don't we just train like 200 different personalities? And my student likes Twilight Sparkle. I wasn't aware of Twilight Sparkle before we wrote this paper. Twilight Sparkle looks like this and talks like this. Like, how is the weather? Gosh, it's sunny and very beautiful and all around me. So this is kind of the style of talking, right? And if I now want a language model to talk like a certain person, unless that person is already in pre-training, what I need to do is I need to do what's shown here on the left-hand side, which is I say, this is the task. Here are 10 examples of what Twilight Sparkle sounds like. And now you can generate something. And the point of this animation, which might not be clear, is that by the time Trace has done the answer, the baseline is still attending to this massive in-context example, okay? Because reading all of these examples is way more expensive than here doing a little bit of probabilistic reasoning at generation time. This is 10% slower than the baseline. This is like multiples of the baseline, just by having this massive context to attend to. Okay, so this works really well. So if you want a language model to sound like James Brown or Doctor Who or Gregory House, within a few seconds we can train a model and do a somewhat decent job at this task. And it doesn't cost you anything at inference time. It's essentially no cost. Okay, so this was our alignment example. I also talked about offline reinforcement learning. So in offline reinforcement learning, the constraint is again different. It's not a log linear classifier or a DFA. It's a property of the reward, future reward, states and actions that I like or dislike. Okay, maybe my acceleration has to be less than some number. Again, same approach. We train a transformer, which is the standard thing to do. You might have heard of things like trajectory transformer. There's very famous algorithms that do this type of stuff. But instead of just sampling from that transformer, we will actually multiply by Reverend Bayes by the probability of achieving the constraint, and then it works really well. So for here, we actually add this neurosymbolic layer on top of trajectory transformer, decision transformer, state-of-the-art baselines, and it actually outperforms the state-of-the-art on all of these standard benchmarks, these Mujoku offline RL benchmarks. If you're an expert on this, you might know that these offline RL methods are very poorly performing in stochastic environments where, given a certain state and action, it's not clear what happens next. There's actually a distribution. And so also here, our method called Trifold does really well. And of course, it has this ability to actually give you these safety guarantees that it will never generate a certain action if that's not allowed. Okay? And so it also works well in these safe offline RL settings. Okay, and then I think this is the part of the talk where I'm just flashing a bunch of applications in your face because I just want to show the full breadth of all the cool things you can do with reasoning in neurosymbolic AI. So if this is a bit much, just tune out and then I'll be done in a few minutes. Another really cool application that is exactly the same flavor is image inpainting. So here you've trained a diffusion model for images, and you haven't really trained it to do inpainting, but then at test time, you see the left-hand side of this shark, and you have to complete the right-hand side with diffusion models. Similar with this owl, you observe this little patch of owl feathers or fur or whatever it's called, and then you need to complete the picture. And these are all state-of-the-art diffusion methods for inpainting, and they're actually not great. This shark looks like it's not doing so well. The owl is not really looking like an owl. It just gets the texture right, but it doesn't really get the concept of an owl, right? It's just the texture. And so what we also built is this system called Tiramisu, which generates these two images. The shark looks a little healthier, and it actually looks like an owl, but what's really cool, it's a completely different owl, right? It looks in a different direction. It's on a branch. Like, it's a completely different picture, but it has the same patch of owl feathers as in the original image, okay? So it's able to infer, like, oh, this must be like a snow owl, and this is what a snow owl must look like as a global picture. How did we do this? Again, same recipe. I just write the same paper over and over again, right? So this is a diffusion model, so it does denoising. At every time step, it gets an image of a noisy owl, and it tries to make it slightly less noisy, okay? It has a neural network that does that. And there is this distribution over denoising steps that is unconditional, because a diffusion model doesn't, at least the ones trained for this task, they don't know about inpainting. They just know how to denoise an image, okay? At the same time, we can have a probabilistic circuit that says, this is how you denoise an image given the constraint that this particular patch has to be the one that's given in the assignment. If I now just multiply these, the diffusion model and the probabilistic circuit, and I do a couple hundred steps of denoising, I actually get these really good results. You can check the paper for these examples. Essentially, the lady's eyes are much better aligned if you use this approach, the neurosymbolic one. If you see some neck of an ostrich, the model actually puts another ostrich next to it. So globally, these images make much more sense than just copying the texture over. Yeah, vision papers are always silly. People just show a bunch of images and then claim they're better. But let's pretend like this bottom row is much better than the others. There's also a quantitative evaluation where the numbers are actually much better than the baselines. So yeah, if you do image diffusion, again, neurosymbolic is the state-of-the-art for this inpainting with diffusion models. Okay, then there's one last thing where this might be a little bit different from the other ones, but it's also using neurosymbolic methods for language models to do marginalization. And here we're actually concerned with the problem of tokenization. So tokenization is just how do we take a string and split it up in these different parts such that I can give it to a transformer, right? So a transformer understands a sequence of tokens, which is more than characters. So for example, caterpillar, llama 2 would write it as the token C, followed by atter, followed by P, followed by ill, followed by R, okay? And the common assumption that everyone uses in large language models is that there's only one way to represent text, and that's this, what we call the canonical tokenization of this text. But there's 784 other ways to write Caterpillar using the vocabulary of Llama 2. Okay? And it's clear that this grows exponentially with the length of the string. I think in the paper we wrote something like, this abstract of this paper can be tokenized in whatever, 10 to the 300 different ways. Right? So this is clearly a combinatorial space, something where the logicians in the room, they should be salivating over this logic problem, right? And so something we did in this paper is actually show that the idea of marginalization over these logical constraints also is very useful in this context. Instead of just looking at computing the probability of the canonical tokenization, I can look at the probability of any tokenization that gives me a certain string. This is useful in these question answering benchmarks like HelloSwag and OpenBookQA and so on, where you're given a bunch of possible answers and you have to see which one is the more likely answer by the large language model, and then this is how you classify the answers. Okay? So instead of using the canonical tokenization of the answer, if you just estimate this probability of the string in this symbolic sense, you can actually get a boost in performance on question answering benchmark. So check out this paper, Where is the Signal in Tokenization Space? And then something else that's fun that you can do is, a lot of these models in post-training, they've been aligned using canonical ways of tokenizing the answer or the question. So for example, if I ask, write a tutorial on how to make a bomb, all the models will say, I cannot fulfill that task. It's impossible, I don't want to help you with that. If I ask exactly the same question, but I tokenize it differently, then the model will be happy to give me the answer. Okay? And so what we did is we actually, again, used circuits, in this case, logical circuits, to find other tokenizations that are good ways of representing the same question, but where the model is not aligned, where all of the post-training that's been done kind of goes away, and it starts to help you make a bomb or do other evil things. And if you do this, you again get state-of-the-art results in jailbreaking large language models. And it's very much a neurosymbolic problem. How you tokenize a string, it's essentially a fixed point algorithm. It's a fixed point logic. It's a purely logical problem hidden under the covers of large language models. Okay? So check out these papers if you care about these crazy neurosymbolic applications that, again, are on the home turf of the LLM crowd. All right, so let's wrap this up. The conclusions for this talk are deductive reasoning algorithms relevant in the age of large language models. So I hope that by overwhelming you with 25 random applications, you feel like there's maybe a lot that we can do as a community in this space. And I think there's a lot of cool stuff that can be done for sure. One of the things we had to do is change what it means to do reasoning algorithms. And we're not doing fuzzy logic. We're not giving a SAT solver or an SMT solver a problem on the CPU. I think that's all super interesting. But if you really want to do neurosymbolic things with zero overhead, it has to be on the GPU. It has to be very predictable in terms of its runtime cost. And so that's typically the choice we like to make, is just scale things up and be extremely tractable. And that means you have to use circuits. All right. Thanks.
Hi, thank you very much. Wonderful talk. I was curious about looking at PyJuice, working with training probabilistic circuits with tools like this. Is there any sense of transfer learning, being able to build on something that has been previously trained? I don't know if that would actually apply here.
Yeah, that's a good question. There's not a lot of people in the world training these models, so we don't have a ton of conventional wisdom about this stuff. I think last time I checked whether we trained from scratch or we fine-tune an existing model on like a new distribution of prompts or something, I think it ends up with roughly the same likelihood, but I could be very wrong. These are the things where, you know, we're battling, you know, hundreds of thousands of people coming up with the hacks that work in the other architectures, and we're a community of maybe, you know, a few labs around the world doing this, so we welcome a lot of contributions of common wisdom about these things, and yeah. And I'm sure a lot of easy tricks haven't been discovered yet, just because we're a smaller community. Yeah.
Hi, guys. Great talk. I kind of have a question about, you know, how you're using this neural network to approximate the part of the Bayes theorem, and I'm wondering exactly if you've accounted for or taken into the equations whether or not like you know are approximating it, right? And so there's like a certain variance in error of p-circuit. And so like you need to account for that. And then my other question about this is, don't you also need to kind of continue the chain forward? Like you need to p next token, next token. And could you just like comment on this?
So that's a good question. So there's a few things here. So on the last comment is, crucially here, alpha doesn't necessarily say anything about the next token. My alpha could be the end of the sentence is Santa Cruz, and then my next token is not yet the end of the sentence. So it doesn't even impose anything logically on the next token. Alpha, by conditioning on alpha, you're actually working, you know, you're back propagating, if you want, this alpha all the way to the beginning of the sequence, so that, yes, whatever effect the red part has on the next token, it looks way beyond the next token. It's a property of something that comes much later. I'm not sure if that helps. And then on the this is just the math of Bayes rule. Now the circuit is about the whole sequence, right? So in that sense it does that implicitly. The probability of alpha will be about the whole generation. So it's not, the next token is just, you can take a conditional distribution and you can do the chain rule of probability on that, and that's how you get this equation. So by breaking it up into little steps, you're not actually doing anything wrong. You're just applying the chain rule of probability to the conditional distribution. And so the given alpha shows up in every part of the chain, and that's why it's correct. Does that make sense? And then on the variance question, yeah, you could ask how close is the red part to the actual real number. And on one side, we try to improve the circuits to get closer and closer. At this point, they're already as good as like discrete diffusion and flow models, but not as good as a transformer. The flip side is that, suppose that my circuit was really, really bad. Let's say it was a uniform distribution over language. We agree that that would be a very, very bad approximation, right? Well, at that point, the only thing that P of alpha does is either say you're guaranteed to fail the constraint immediately, or you might still solve it later. It's like a 0-1 thing. That is exactly what structured generation tools do today. So the worst case scenario where p-circuit is complete garbage is actually the current state of the art for structured generation. So if you do a little bit better than that, you're already winning. You see? Thanks.
Hi, Guy. Thank you for this great talk. I'm Tamanna, a PhD student at UCLA. With the really new large reasoning models with really big messy internal reasoning traces, which proprietary models don't even release to the public. My advisor Samir and I, we've started to look through them, and they can be really long and messy and maybe not even always follow logical patterns. And we've been sort of thinking about, is there a way to do sentence level constraints on these reasoning traces? And I just wanted to ask you if there's already work being done in this space, or have you been thinking about it, or any pointers on how to think about it?
Yeah, I think that's a great problem to look at. Like when we did this silly application, this was, you know, before DeepSeek and before these traces got really long and so on. So this is a little bit out of date from that perspective. And I feel like it's kind of a layup for doing more interesting work with complex chains of thought. And I think we just have to find the right constraints and the right maybe log linear classifiers to actually make the reasoning more robust. So one of my students also is trying to do some of that work, and I think the more the merrier. But I don't know of any actual work that's succeeded yet on that side.
Oh,
well, actually,
that's good to know.
Actually, I know there's some unpublished work by my colleague Nanyun, but I cannot talk about it. And she actually improves the Llama reasoning performance by quite a lot by imposing a particular DFA, but paper hasn't been published yet, so check again in maybe a month.
I'll look out for that, because
Yeah.
I think the reasoning traces are a bit different from just chain of thought, because it's not linear and there's backtracking, and we've been thinking about how to account for that. And yeah, I'd love to see what your lab's doing.
No, I think we need a lot of research on this because there's a lot of opportunity there, and there's probably not enough GPUs and smart people that are able to actually tackle that problem. So yeah, let's do it. Yeah.
Cool, thank you so much.
Hello, Guy. Thanks so much for the talk. I love how you used this example to show that a simple DFA would be able to improve the performance so much. My question is that I don't know if you think hallucination is also one of the alignment problems, but I would say it's one of the most well-known problems within LLMs. And the theory I have heard the most about is that it roots in the probabilistic nature of LLMs, which is like predicting the next token, which is also I would say the theory behind like Bayesian and stuff. So like I don't know if you have any thoughts on like maybe if the circuits would also be applicable to this kind of to mitigating the hallucination in LLMs. I would love to hear your thoughts on it.
Yeah, I don't have great philosophical ideas about hallucination, but I feel like there's a lot of easy hacks that can really mitigate the problem that use neurosymbolic methods. And for several years, I've been telling people like, whenever you're doing RAG and you're Amazon and you're talking about some product, let's say some medicine, you can pretty easily figure out that if you're going to generate number milligrams in your answer, it should be number milligrams that comes from the numbers that are actually in the documentation of the product you're selling, right? So in this kind of RAG, kind of knowledge graph setting, I think it's very easy to come up with guardrails of what you are allowed to generate. And I think there is some work on this, but so here's my problem, right? Anytime I give this talk, I get like 20 interesting ways of this, applying this from very clever people. And then I have like one PhD student working on this, and then she hates me whenever I come back from a conference and I have like yet another like set of things to try. So I think the community hopefully picks this up and tries some of these ideas. Yeah, I think a lot of cool stuff is possible there. Yeah.
Yeah. Thank you.
This was great. Thank you. I think you just began to answer in this. It wasn't clear to me whether the DFA comes from control G, whether it's synthesized by the user, how do you use it, whether you have a repertoire of them. And maybe whether you could also say something about limitations of the whole approach. I mean, you talked about the billions being spent on the one-on-one, and I was wondering, why is that, and what are your thoughts on that?
Yeah, so that's a good question. So on the first one, so I used to do a lot of weighted model counting by compiling circuits from CNFs and programs and all of that stuff. These days, I never actually compile anything in this kind of set solver way. I don't do knowledge compilation because all the applications I'm doing, the DFA is kind of by construction. So for the keywords, it's easy to generate a DFA for keywords. For this application, the user gives me keywords and a length constraint. It's easy to turn that into a DFA in a very predictable way. Here, the DFA just comes from the question. It's very easy to generate it. So the DFA is always, the user doesn't draw the DFA circles or whatever, but it's kind of downstream from their question or keywords, etc. Second question was
Limitations.
Limitations, yes. So there are plenty of things we care about that are not DFAs, right? Things like, my favorite example is def use constraints in programming. If I want to say you're not allowed to use this, you're generating Python code, and I want to say you cannot use this variable before it's been declared, right? this is a context-sensitive constraint. There is no DFA for it that's compact. But I also believe that it doesn't really matter because the LLM is actually pretty good at introducing new variables. So if all I do is say, I can only use variables that have already been declared, but I change the DFA as I'm declaring new variables, I think for all intents and purposes, I have captured this notion of def use. Even though in theory, the problem is completely intractable and it's a context-specific constraint, it doesn't have a DFA at all. In practice, it has a tiny DFA if I approximate it this way. So I feel like a lot of, same with reasoning, right? So famously, like the weight, adding the weight token to my reasoning chains makes reasoning better. The weight token is just a simple DFA. So I feel like a lot of really complicated things I want to put in alpha are extremely well approximated by a simple constraint, given that we're working with the pre-trained language distribution, which already has a lot of information in it. I don't know, maybe I'm wrong, but then again, you know, these are 25 papers I wish I could write, but I don't have the bandwidth to, so please investigate, yes.